Okay, YouTube, in this video we're going to be exploring again how to solve logarithmic equations, but a special instance in which we cannot isolate the log, get it by itself on one side because of the fact that we have two or more logs that are present. So what we're going to do if we have more than one log present is use the properties of logs in order to rewrite this as one log. So we're going to use the properties of logs to rewrite these as one log. A single log. So what I want to do really quickly is kind of list the properties we have here, but we have a product rule, a quotient rule, and we have our power rule. So I'm going to make sure that we list these over here. But these rules essentially say that if you were to have a log, we'll call it base b of a product. And we could rewrite this as log base b of the first factor in the product plus log base b of the second factor in the product v. With our quotient, same story, but because we're talking about a quotient, we're going to do the inverse of addition here. We're going to get log base b of everything on top, u, minus log base b of everything on bottom, b. And then our last property here says log base b of u to the n power. We can pull that exponent out in front and call this n log base b of u. So in this particular case, what I'm going to tell you is that when we rewrite expressions like these three here as what you see on the right, that's called expansion. But when we write these three expressions on the right as these over here, we refer to this as condensing. So the idea is, if my job is to get the log by itself, then perhaps we can condense these two logs into a single log and then rewrite this. So what I notice is that these are both base 10. We could even write it in here, log base 10, both common log. But because I'm adding them, what this means is we have a product property. So I'm going to rewrite this as a single log base 10 of the product of these two things. And what I get is x times x minus 3 on the inside. It equals this. So to show you how this is helpful, what I'm going to say is, well, now I've got a single log by itself on the left. We could rewrite this into exponential form. So what we discover is this. 10 to the power of 1 equals x times x minus 3. So in any situation like this, of course, what we could do is we could distribute, set it equal to 0, so let's subtract 10 from both sides here. If we do this, we would get 0 equals x squared minus 3x minus 10. And then we could solve this by factoring. So I notice that this does indeed factor. We could say x minus 5, x plus 2. And if those are our factors, of course we know because these are our linear factors, then our solutions are x equals positive 5 and x equals negative 2. So these two solutions, I would encourage you to try them in the original equation. Now, the reason why I mention this is because in this particular case, I got two answers, 5 and negative 2. Let's try 5. We have log base 10 of 5, place log, sorry about that log there, log base 10 of 5 minus 3 equals 1. So I get really log base 10 of 5 plus log base 10 of 2 is 1. Okay. So in this particular case, if we were to rewrite this now as a single log, just to show you this works here, we get log base 10 of 5 times 2, which is really log base 10 of 10. And of course, anything to the first power equals itself. So the 5 works. Now what I want to show you is this. We take log of negative 2 plus now log of negative 2 minus 3. Does that equal 1? What we're going to say here is this. These cannot be negative. Cannot be negative. And so what this means is the solution negative 2 is an extraneous solution. It is an extra solution. Remember that if we were to have an expression like log of negative 2, what we'd really be asking is this: what could I take 10 to the power of to get negative 2? And this right here is impossible. So that's why we can't include any negative arguments inside of our logs. Cheers.